Hello, I welcome you all to this another interesting screencast. The problem reads the cable is subjected to the triangular loading. If the slope of the cable at point O is 0, determine the equation of the curve y equal to f of x, which defines the cable shape OB and the maximum tension developed in the cable. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. We have a cable which is symmetrical about the y-axis. Both the geometry and the loading is symmetrical. And that is one of the reasons why it has been suggested in advance in the problem. And the axis has already been given to us at the point O where the slope is equal to 0. The slope of the cable at point O is equal to 0. We are being asked to determine the curve y equal to f of x, which defines the cable shape OB, and the maximum tension developed in the cable. One of the ways we can define the maximum tension is just by applying the equations of equilibrium for OB. We could get just OB the way it is. Okay, so imagine this is O, this is our TO there, and then we have B, this is our TB there. Okay, with the slope which is unknown. The slope there at O is 0, and then we have the loading like this, and we know the maximum intensity there of 500 pounds per feet. Okay, so we can use this part just the way it is, all right, and apply the equations of equilibrium. We have how many unknowns? We have TO, we have TB, we have theta. This is already given. The h is 8 feet, or the maximum side. So with this information, with three unknowns, we have three equations in 2D, equations of equilibrium. We're able to solve all these unknown quantities, TO, TB, and theta. And when we solve all these quantities, we'll end up finding the maximum tension, which will be TB, because this is where we have the maximum angle at B. So, and we are also able to find the horizontal component FH, okay, which is constant throughout the length of the cable. But for us to find the function y equal to f of x, we'll need to use the differential equations that defines the shape of the cable under this uniformly distributed load. In this case, a triangular loading, but it doesn't really matter. So like I'm saying, we can use the equations of equilibrium, but for the equations of equilibrium, you can only determine the maximum tension. But let me use the other method where we are going to still find the maximum tension as well as the equation of the curve y equal to fx. Right. Again, these equations were determined by cutting a section, an infinitesimal section of the cable subjected to distributed loading, and then later on applying the equations of equilibrium. Okay, and the following equations were determined or developed. So we have d t cos theta dx equal to 0, which finally gives us, if we did the integration, t cos theta is equal to a constant Fh, which is the horizontal component of the tension in the cable, which is constant throughout the whole length of the cable. And then we have T sine theta dx, which is equal to the distributed loading. What does this remind us of? Remember, dV dx equal to the loading in a beam, right? If we integrate this, then we have T sine theta is going to be equal to the integral of the distributed loading. And then finally, we have the dy dx, okay, which defines the slope of the cable, all right, which is equal to tan theta. If we are to combine these three equations, then we develop one equation that defines the curve of the cable shape, which is equal to y 1 divided by fh double integral, okay, double integral of w dx close brackets then dx. So this is the equation that we are going to use. And I'm pretty sure this introduction you are already conversant with. So we are going to use this equation. In our case, W, okay, since it is triangular in load, so you expect it to have a slope. So this is going to be equal to m, which is the gradient mx plus c. But we know that c is equal to 0, and our gradient there is the change in the y, which is 500, divided by the change in x, which is a 15. Therefore, our loading is going to be equal to 500 divided by 15. We're just using this portion there, right? 15x, okay, like so. So this is the loading that we are going to integrate. So let's replace this loading in our curve, in our function, the y of x or f of x. So y is equal to 1 over horizontal force, and then we have the integral in brackets, then we have our distributed force, which is triangular, 15x dx, then dx. Right. So now let's integrate this, okay, as an indefinite integral. So y is going to be equal to fh. Okay, if we are to integrate this one, then we are going to have 500 x, we are integrating inside, x squared divided by 2 by 15, which is a 30, okay, plus c1, okay, because this is an indefinite integral, we don't have the constants there, then dx. Right? And then we do the second integration again. So we have fh, okay, so this becomes a 500 x cubed, then 3 by 30, which becomes a 90, then plus c1x plus c2. Right. So now we are at this particular stage. Let me just get rid of this information here. We are at this particular stage. So we'll need to find this integration constant. But before we do so, let me also find the first derivative of this. I write it in advance. Okay, dy dx, which is just equal to fh. Okay, then this becomes 500 x squared, okay, divided by 30, okay, plus c1, Okay, so I'll need this because I'm going to use these two equations for me to find these constants C1 and C2. So let's look at the boundary conditions at point O and B, since we are just looking at one segment, because this particular system is symmetrical about the y-axis. So what are the boundary conditions at point O? We know that when x is equal to 0, y is equal to 0. This is one boundary condition. And again, when x is equal to 0, dy dx is equal to 0. This has already been given to us in the problem. We are told, right, to say the slope of the cable at point O is 0. So with these two boundary conditions, let's now find the constants C1 and C2. So let's use the first equation, okay, and plug in the first constant, x equal to 0, y equal to 0. If we did so, we have y equal to, okay, y is 0 equal to 1 divided by this constant fh. Then we have a 0 plus a 0 plus c2. Therefore, c2 is equal to 0. Okay, let's use the second equation with these boundary conditions. So we have 0 equal to 1 over fh. Okay, what do we have there? X equal to 0, this is 0, then plus c1. Therefore, c1 is equal to 0. So both c1 and c2 are equal to 0. So let's rewrite this particular equation. C1 and C2 is equal to 0. C1 and C2 are both equal to 0. Therefore, y will be equal to 1 divided by fh 500 x cubed divided by 90. Okay, is that fine? Great. So this is almost done, but we're not yet done because we need to find FH. FH is the horizontal force or horizontal component of the tension force in the cable, which is constant throughout the length of the cable. So let's find what this value is. Right. So what is this FH? This FH, we are going to use another boundary condition at B. At point B, we know that x is equal to 15, and therefore our y at that point is equal to h, which is equal to 8 feet. So with this information, we can plug it in there. I will say 8 is equal to 1 over fh, alright, then 500 times 15 to the power 3 divided by 90. Therefore, fh, if we made fh subject of the formula, this becomes equal to 1 divided by 8, 500 times 15 cubed divided by 90. What does this give us? Let's grab our calculators. 500 times 15 cubed divided by 90 divided by 8. So we have a 2343.75. Let me come again. 500 times 15 cubed divided by 8 by 90. 2343.75. So this is our FH. Therefore, y is equal to 1 divided by 2343.75 times 500 x cubed divided by 90. We can simplify this further if you want to. So we can do so. Let me just clear my space here. Okay, 234375. Okay, so let's simplify this further. So this therefore is going to be equal to, if we simplified it further, then it will give us a value of, then our y is going to be equal to 500 divided by 2343.75 times 90. Okay, not a very good value. I think I'll leave it the way it is. I think this is fine. I'll just leave it like this. So this is, if you want to simplify it, you can simplify it further, but I'll leave it like this. So this is the function that defines the cable shape. We've been also asked to find the maximum tension. So we want to find that the maximum tension is at the point where we have the maximum angle. And we know that the maximum angle is going to be at B. Okay? And we are going to use this equation T cos B. The T cos theta is equal to FH. So we know our FH already. FH is equal to 2343.75 pounds. And we don't know what this theta is. We can calculate it using this equation, the same equation that we found, right? So let's convert this to a slope function. So dy dx is going to be equal to 1 divided by 2343.75. Okay, then 500 x squared divided by 30. All right. So now we are going to plug in the value of x, okay, which is 15. So we'll say our dy at 15, okay, at x equal to 15, so that we find that angle. So 500 times 15 squared divided by 30. So let's find that value. So this is 15 times 15 squared divided by 30. Okay, 500 times 15 squared divided by 2343.75 times 30. So we find a value of 1.6. All right. So tan theta B is equal to 1.6. And therefore, theta is going to be equal to arctan of that. Arctan of 1.6 gives us a 57.99, which is a 58 degrees. So now, using this equation here, let's find the value of, and this is our maximum theta is equal to 58 degrees. Therefore, T max is going to be equal to T as a function of 58 degrees is equal to FH divided by cos theta max, which is equal to 2343.75 divided by cos 58. T max therefore is equal to 2343.75 divided by cos 58. So we have a value of 4422.84 pounds. Let me check it. 2343.75 divided by cos 58. 4422.84. Okay. So finally, let me write down the summary of the solution. So we have Tmax is equal to 4422.84 pounds. And our horizontal force, of course, I'll indicate it also, is 2343.75 pounds. And our maximum angle B, which is maximum, we found it as 58 degrees. I think this is about it. This is about it. Let me just create an outline. This is about it. We are done for this particular problem. We have found the curve or the function that defines the cable shape OB. We have found the maximum tension force in the cable. And of course, we've also included the horizontal component as well as the angle at B. And since this is symmetrical, we expect similar results even on the other side. And I hope the video was helpful. If it was, give me a thumbs up, like my video, and continue subscribing. Bye-bye, and see you in my next screencast.